what is covered on test two? Test two covers from, what do we call that? Pigeonhole principle. So from here all the way up to independent events. Okay, so basically up till up till the 10th. Infinite sample spaces, random variables will not be on this test. Yeah, so basically it's going to be a lot of recursion and a lot of probability. And I don't know. I think it'll actually be good. I mean, you know, nobody wants to write a test, I suppose, but it's excellent practice for the final exam. You guys will have seen, you know, 3/4 of the questions are the types of questions that you're going to see on your final. Yeah. Yeah, old finals are better. And basically the middle, like half of the old finals. I would go to the finals, I would skip all the counting, start with the recursion questions, into the probability. Once you see expected value or random variables, you've gone too far. I'm actually going to take up some questions from one of them today. So yeah, that's, I guess, what would you guys prefer to take up the questions first and then continue on the lessons, or vice versa? Questions first, yeah. So you guys are nice and fresh for the yeah, okay, so we'll do that then. Yeah. Other questions before we start looking at this? Okay, again, grade scope, I will give you more details as we get closer. For now, it is going to be, the nice thing about it is you'll be able to, we scan all of the bubble sheets in and you will be able to see them. You see your test online. You won't have to come to my office. You can just, you can come to my office or email me if there's a problem. So yeah. Okay, so here I have a test from winter 2019. This is the final exam. And here, so counting is up until question 7. There's no pigeonhole principle on this one, right? I think in some sense, pigeonhole principle is sort of very straightforward. But starting at question 8, we have recursion. And Fibonacci is a good sign that we've entered recursion. Gotta think, yeah, I think I covered everything. Okay, so let's look at question 8. Question 8 is, I have a bit string. It's called 0, 0 free if it does not contain 2 zeros next to each other. So we've looked at 0, 0 free bit strings in class. And what we found is that if I have a 0, 0 free bit string of length m, then the number of those types of bit strings is equal to the m plus second Fibonacci number. Okay. So now we're going to count the number of 0, 0 free bit strings of length 20, but 0, 0 free bit strings of length 20 that have a 1 at position 11 and a 0 at position 20. Okay, so we see and here, so that's going to be both of these things are true at once. You know, I could say or something like that. But yeah, so let's take a look at, so these questions are nice because they're not that difficult, but they rely a little bit on thinking the same way we did when we took up these 0, 0 free bit strings. So I'm just going to start listing off 1, 2, these are the positions in my bit string. And then it says I have a 1 at position 11. I'm going to say this is 10, 11, 12. And then I have a 0 at position 20. So we'll say 19 and 20. So this represents my bit string, and I'm going to look at, you know, I'm going to put a 1 at position 11. So there's a 1 that goes here and a 0 at position 20. So now how many 0, 0 free bit strings do I have that look like this? Okay, so then the trick is as follows. I have a 1 here. Well, if you recall, when we counted our number of 0, 0 free bit strings, we broke them down into 2 sets. One that started with 1 and one that started with 0. And if it starts with 1, then I can put anything in the next location. right? I'm not restricted at all because it's 0, 0 free, but it doesn't say anything about the ones. So that means in location 10, I could put a 0 or a 1, it doesn't matter, which means from locations 1 to 10, I can put 0 or 1 as long as it's 0, 0 free. Okay, so that means the number of 0, 0 free bit strings. Well, for starters, it's the number of 0, 0 free bit strings of length 10, which is the 12th Fibonacci number. Okay. So does that make sense? I'm just counting the number of 0, 0 free bit strings of length 10, because that's what will fit in here. And I can accept any of them as long as they're 0, 0 free, because I know there's a 1 at location 11. Okay. So length 10, don't forget to convert from, it's a 0, 0 free bit string of length 10, but it is the 12th Fibonacci number. Don't forget to do that conversion. On the other side, well, at location 12, again, I can put whatever I like. It's a 1, I could put a 0 there or a 1 there. This 0 causes a little bit of problems. If I have a 0 there, then I can't have a 0 at location 19. So that means I must have a 1 there, which means that, well, then left of 19, say, we'll put in location 18 here. I can put whatever I like as long as it's 0, 0 free. So then I want to look at these positions, and there are, let's see, 7 of them. And as long as it's a 0, 0 free substring of length 7, then I'm okay. And there are 9 of those. Okay. So that means the number of, I don't have the answers, but the number of 0, 0 free bit strings of length 20 that have a 1 at position 11 and a 0 at position 20 is F9 times F12. Right, so it's the number of 0, 0 free bit strings here times the number here. Just product. Right. Questions? These are good. I really like these because they are simple enough for an exam, but they are still recursion. Okay, so related to that, bit strings that do not contain 0, 1, 1, and they have a 1 at every even position. Positions are numbered starting at 1 again, so let's just put a bunch of blanks. Position 1, 2, 3, 4, 5, etc. And I have a 1 at every even position. So I have a 1 here, a 1 here, put a 6 here. Yeah. So it's going to look something like that. And it does not have 0, 1, 1 anywhere in this string. So what does that mean? Well, again, I'm simply going to start by figuring out, I'm going to, put a 0 or a 1 in the first location and then kind of see what happens. Right. So I could start by saying, well, what if I put a 0 here? Well, then what happens? What's that? 3 has to be 0. Yeah, because I cannot have 0, 0, 1 in this bit string. So it does not contain 0, 1, 1. So that means 3 has to be a 0. Well, what if 3 is a 0? Yeah, then 5 has to be a 0. And basically every odd number has to be a 0. So yeah, that's awkward. There's really only one string that matches that description. Okay, so that means whatever Sn is equal to, there should be a 1 in there. And then I'll look at, okay, well, what if I start with a 1? I know which bit string, which bit is in location 2. And then, well, everything else after that, as long as it's 0, 1, 1 free, is okay. Since I have n-2 positions left, I'll form that recursively and I'll say, well, it's, if I have a 1 here, then it's really the number of 0, 1, 1 free bit strings with a 1 at every even position of length n-2. So yeah, that means B would be the answer. And I don't have the answers in front of me, so think critically, double check my work. These I'm pretty sure are correct. All right, questions? Okay. This question 10, this is simply induction, proof by induction, but I mean, what you want to do right away is eliminate as many as you can using the base case, right? So I want to, given that I have a base case and a recursive, a recurrence essentially, I want to prove that one of these is the closed form. So f of 0 for A is equal to 5/2 3 to the power 0, which is 1, minus 1. So this is basically 3/2. And I need f of 0 to be equal to 2, so I can rule out A right away. Okay, so this is not the answer. 3/2, 3 to the n minus 1/2. So 3/2, 3 to the power 0 is 1, and then minus 1/2. So 3/2 minus 1/2 is equal to 1. Okay, so I can rule out B actually right away, very easily, just using the base case. Okay, so now I have a choice between C and D. Let's try C, 5/2, 3 to the n minus 1/2. Well, that's actually equal to 2. Right. So the base case is okay for C. Now I just have to check this recursive case. Okay, so, all right, questions so far, everybody okay? Base case, yeah. Okay, so now I'm going to write down my recurrence, but I'm going to substitute my closed form. I'll do it, and I won't skip any steps here. So this is equal to 3 times, and then f of n minus 1. I'm just substituting this in. So this is 5/2 times 3 to the n minus 1 minus 1/2 plus 1. Okay, so I just substituted n minus 1 in for n, and I substituted this in for f of n minus 1. And then it's a bunch of algebra. Try not to make any mistakes. So this is, well, 3 times 5/2 times 3 of n minus 1 is simply 5/2 times 3 to the power n. Right, so I'm running a little bit out of space here. I'm going to steal some. So 5/2 to the 3, 3 to the power n minus 1/2 times 3, which is 3/2 plus 1. That's the plus 1. Minus 3/2 plus 1 is equal to 5/2 3 to the power n minus 1/2. And that does give me back this closed form. So that means C is the correct answer here. All right, questions? We flip a fair coin 6 times. The flips are independent. What is the probability that in these 6 coin flips, the coin comes up heads exactly 3 times? All right, so there's a bunch of different ways we can solve this. Let's start with the sample space though. So the sample space is I flip the coin 6 times, and this is it could come up heads or tails, and this is a uniform probability space. Okay, so we can say that, well, the sample space is, I have 2 choices for each of these 6 flips, and I have 6 flips. I believe that's 64. Okay, so now I want this event A is that heads comes up 3 times. So now, since it's a uniform probability space, I could just count, well, how many ways out of 6 possible coin flips can I have 3 of them come up heads? How many ways is that? Yeah, so this is 6, choose 3. All right, so it looks like we're going to be simplifying a little bit. So you will get, what do we have here? You don't really need this. You don't really need, maybe I give you that though. No, you don't really need that. So I give you this and this, I believe. So you'll get those. So you can look back here if you want the formula for the binomial coefficient for n, choose k. Right, so we go back, we can substitute that in and try and simplify. So the probability of A equals 6, choose 3. Well, that's 6 factorial over 3 factorial. 3 factorial. I'll go get a slightly thinner. Okay, so that's over 64. And that's equal to, well, I can cancel out one of the 3 factorials and I get 4 times 5 times 6 over 3 times 2 times 1, basically, over 64. All right, so 3 times 2, I'm doing this in a lot of extra detail, but so this is 6 over 64. This gets canceled out. I'm left with 20 over 64. Or, well, another way to look at it, actually more accurately, I suppose, is I can cancel this 4 with 4 from here. So 64 divided by 4 is 16. It should be 5 over 16. Okay, if you have a calculator, which you're allowed to have, you can just punch it in also. Yeah, so the answer here is C. Okay. All right. Standard deck of 52 cards. All right. So this is the probability that I get 3 aces and 2 queens in a hand of 5 cards. If I look at the answers, they're all 52, choose 5 for the base. That is, of course, the size of my sample space. So now I just need to count the number of hands with 3 aces and 2 queens. So let's call that, well, we'll call it A, but so the number of ways I can choose 3 aces out of 4 is 4, choose 3, right? Or simply 4. Let's do it in all of the detail for now. The number of ways I can choose 2 queens is 4, choose 2, right? This is, I'm just straight up using the product rule. I happen to know that 4, choose 3 is 4 and 4, choose 2 is 6. So that's 24. So that would be A in this case. Hopefully. I think I did that right. Yeah. Great questions. Pretty straightforward. Conditional probability. I flip a coin 6 times. The flips are independent. What is probability of A given B? So that is probability of A intersect B over the probability of B, right? So that's our definition. What is A intersect B in this case? Well, I have exactly 3 flips that result in heads, given that at least 2 flips result in heads. We can simplify this a little bit, right? So what is A intersect B? Well, we don't know that they're independent. So the flips are independent, but these events A and B are not necessarily independent. In fact, they're not independent at all. Yeah. However, what do we know if I look at, let's say I look at all of the flips. This is my sample space. I look at, this is at least 2 flips result in heads. And then I look at, so this is B, and then A is actually contained in B. All right, so in this case, A intersect B is simply A. Right, if I take all of the flips that I have at least 2 flips that result in heads and exactly 3 flips result in heads, that is simply exactly 3 flips result in heads. Okay, so this is equal to probability of A over the probability of B. This is a uniform sample space. So independent, they're fair and independent gives us that it's uniform. So we can, in some sense, you know, this is going to be the size of A over the size of the sample space over the size of B over the size of the sample space. We can, sample spaces will cancel out. So we're left with the size of A over the size of B. Okay, so the size of A, exactly 3 out of 6 flips result in heads. Well, we already figured that out. That's 6 choose 3, right? I simply choose 3 of those coins. The size of B, at least 2 flips result in heads. This is a little bit trickier. I actually do need that sample space now. So my sample space is size 64, right? We computed that in an earlier question, all the ways that I can flip 6 coins. And I'm going to use the complement rule here. So at least 2 flips results in heads means I'm going to take the size of B is equal to the sample space minus exactly 1 flip results in heads minus exactly 0 flips result in heads. Okay, so exactly 1 flips results in heads. That is what? How many different ways can I flip 6 coins with 6? Yeah. And all I'm doing is I'm simply choosing where the heads comes up, which of the 6 positions. So this is minus 6. 0 flips come up in heads. How many ways can I do that? Yeah, 1. So yeah, that's nice. It's nice that 64 minus 6 minus 1 gives us 57. That's a good hint that we're on the right track. So this is 6 choose 3 over 57. 6 choose 3 is, I forget off the top, what is it, 20 over 6 or something? I don't know. 6 factorial over 3 factorial, equals 4 times 5 times, yeah, so it's 20. Yeah, 4 times 5 times 6 over 6. So then the answer here is D. All right. Yeah, this one's, so 14 is kind of nasty. So let's, so we have 2 bit strings. They're both random. They both have n bits in them. And then we define, so we define these, each of the individual bits in string A by AI, and each of the individual bits in string B by BI. And then we define this number CI, which is AI minus BI. And then we want to find all of the locations or all of the variables CI that are greater than or equal to 0. So let's just take a quick look at what this results in. Okay, so I want all combinations of AI and BI. AI and BI are just individual locations in my bit string. So there is 4 possibilities. Right, so BI can be 0 and AI 0, or AI 0, BI 1, AI 1, BI 0, or both can be 1 because they're 2 separate bit strings. And each of these, again, you can compute it. Since they're independent, then the probability that this is a 0 is a half, and the probability that this is a 0 is a half. So that is probability 1/4 for each of these outcomes. Or you can, it's a uniform probability space, again, because they're fair and independent coin flips that decide on these bits. So AI minus BI is 0. AI minus BI here is -1. Here it's 1, and here it's 0. So I want to look at every location where CI is at least 0. So out of the 4 possibilities, I have 3 of them, right? So this one, and this one, each has a probability 1/4. So I know that, you know, the probability that CI is greater than or equal to 0 is equal to 3/4. And then the probability that CI is less than 0 is equal to 1/4. Right, so that's any individual location in my bit string. This is again, this is a little bit nasty. If you practice, questions like this, then it becomes easier, but all right. Questions so far? Okay, so now I want the probability that the set P is equal to K. So this is the set of all of the locations CI for which, the value is at least 0. Okay, and we see it's 3 out of 4 or with probability 3/4. And we want to find the probability that that set is equal to K. All right, so I'm going to use the, these are independent. So CI, the value of CI is independent. So I have K of them that come up with probability 3/4. Right, so I want to find the probability that P is equal to K, or the size of P is equal to K. Let's just write it like this. So I have 3/4 with probability 3/4. CI is greater than or equal to 0, and there's K of those. Right, so that's simply the product rule, or well, they're independent, so I'm going to multiply them together. In some sense, those are sort of equivalent statements, but and then I have, well, if I have K that are greater than or equal to 0, I have N minus K that are less than or equal to 0, or sorry, less than 0. And those come up with probability 1/4. That's for a given string. Now I have to count all of the ways that I can have K of them, K of these locations greater than or equal to 0 out of N, which is simply N choose K, right? So maybe this one, this one, this one. There's N choose K ways to do that altogether, right? So then I have, this is times N choose K, or, usually you would put that up front. So here it would be B. That one's a little bit harder, but next questions. Okay. All right. Independence. So consider a uniformly random permutation of these 5 numbers. A is the event. A1 is odd. Somebody does have a question? 623. No one answer. B is the event. A5 is even. So we want to determine if they're independent. They are independent if this is true. Okay. So all of the permutations, how many permutations do we have of these 5 numbers? So what's our sample space? 5 factorial, yeah. So all of the permutations of a set of size 5 is 5 factorial. So our sample space has size 5 factorial. It's a uniformly random permutation, so this is a uniform sample space. So now I just want to count A intersect B, A and B, and then I can find the probabilities. So let's look at A, the size of A. A is that A1 is odd. I'm just using the product rule here. So the number of ways to choose an odd number for the first location is what? 3. Yeah, so I have 3 choices for the first one. And then I don't care what the rest of them are. So how many ways are there to choose that? I have 4 numbers left, and I have 4 locations to put them in. Any permutation will do. Right, so this is 4 factorial. Okay. The size of B, similar. A5 is even, so I have 2 choices there. And again, I have, once I set the 5th location to that number, then I have 4 numbers left and 4 locations. So there's 4 factorial ways to do that. Okay, so yeah, wish I had more space. Let's do that. Okay. Now I want A intersect B. So A1 is even and A5 is odd. So again, for A1, I have 3 choices. For A5, I have 2 choices. And now I have 3 numbers left and 3 locations, and I just want to take all permutations. So that's going to be 3 factorial. All right, so then probability of A intersect B equals 3 times 2 times 3 factorial over 5 factorial. That is 3 times 2 over 4 times 5, which is 20. Yeah, so it's 6 over 20. And now, is this equal to probability of A times probability of B? It's equal to 3 times 4 factorial times 2 times 4 factorial over 5 factorial times 5 factorial. So let's cancel some of this out. This cancels with that, I have 5. This cancels with that, I have 5. So this is equal to 6 over 25. So they are not independent because the probabilities don't match. So the answer here is B. It's not none of the above or all of the above. That's a little joke McKeel used to like to play, because there's only 2 possible answers. This is basically a true or false question. Yeah.
And you're not taking the side of A divided by the side of B divided by the.
I mean, that's how you get the probabilities, right? So I sort of did all that in one step.
So can we just directly come to the conclusion of deciding A and B is not the same, then they're not.
No, because you have to multiply them together, right? And then there's, I mean, potentially, I mean, you can, at some point you might just spot it, right? That they're not going to be equal, but yeah, in this case, they're pretty close, right? 6 over 20 and 6 over 25. So yeah, A and B don't have to be the same. They don't have to be the same probabilities. They just have to multiply to be equal to this. All right. Other questions? Okay. You roll a red die once and a blue die once. How did we get A and B again? The size of A and the size of B was counting. So A is the event that the first letter in my permutation was, or sorry, the first number in my permutation was odd. So that means I put a 3 here perhaps. Right, I have 3 choices of odd numbers that can be 1, 3, or 5. Once I put 3 there, I have 1, 2, 4, and 5. I have 4 locations, and any order will do. So there's 4 factorial ways to arrange them there. And then I do the same thing for B. B is that the last number is even. I have 2 even numbers, 2 or 4. And once I do that, I have 4 factorial other arrangements. Okay. Roll a fair red die, a fair blue die. These rolls are independent. We have 2 events, and again, it's going to be probability of A intersect B equals probability of A times probability of B. Now, obviously, you guys can do what you like, but whenever I do these questions, even just to prove them to myself, I always start with the formula. It's always good to know exactly what you're trying to prove and exactly what information you need to, either prove or disprove this. Okay, so probability of A intersect B. Well, let's do probability of A first. The sum of the red die and the blue die is 5. So 2 dice, it's a uniform probability space. Each of those has, well, the size of the sample space is 36. Right, that's 36 possible outcomes. So how many of those sum to 5? Well, I'm just going to list them. I don't really want to, So 1 and 4 sum to 5, 2 and 3 sum to 5, 3 and 2 sum to 5, and 4 and 1 sum to 5. So there's 4 possible outcomes. You know, if the left is the red and the right is the blue. So this is 1/9. Okay. Probability of B is the result of the red die is even. We can cheat a little bit there, right? So we only care about the value of the red die. What's the probability that it's even? So I have 6 possible outcomes for the red die, and 3 of them are even. So it's 3/6 or 1/2. Okay, so then probability of A times probability of B is 1/18. Okay, 1/9 times 1/2. So now I just want this. So, well, I can take advantage of the fact that it's a uniform sample space. So this is 36. How many outcomes are in A intersect B? Well, I erased all of my outcomes, so let's put them back here for A. So 1 and 4, 2 and 3, 3 and 2, and 4 and 1, where the left side is red and the right side is blue. And then I want the intersection of that with the result of the red die is even. What did I say? The left side is red, so that's this one and this one. So there's 2 possible outcomes for A intersect B. Right, so that's 2/36 or 1/18. So yeah, in this case, they are independent events. Questions? Okay, how are we doing? All right, well. We were just on time up till now. I'm sure we'll catch up again. So this is 17. This one's a little bit hairier. Maybe there's a simpler solution, but I couldn't think of one off the top of my head. So let's take a look at it. I have a uniformly random permutation of n numbers, and event A is A7 is the minimum of the first 7 numbers. And event B is A6 is the minimum of the first 6 numbers. All right, so again, I want to prove or disprove this. So let's just start with the easy stuff. Probability of A. It's going to be a little ugly. Of course, it simplifies really nicely, but let's take a look at what we would have to do. So I have n possible numbers. I take a permutation. So now I want the number of permutations where A7 is the minimum. We did something similar before. So what I'm going to do first is I'm going to choose 7 out of those n numbers. So this is, yeah, let's say size of, we'll come back to that. We're just going to count the size of A right now. So it's n choose 7. I choose 7 numbers, and then I put the lowest one in location 7. Right. So I need 7 numbers to know that out of those 7, there is definitely, you know, the lowest. There's one way to do that, and then there's 6 factorial ways to arrange the other 7. Right. So let's take a look at what I'm doing exactly. This is number 7. I put the lowest number here. The other 6 numbers that I've chosen, I arrange before it. Right, so just 6 factorial ways to do that. And then there are n minus 7 numbers left. Right, that's if I look at these, and there's n minus 7 locations, n minus 7 numbers. So I have n minus 7 factorial permutations. Okay, so that's the size of A. It's a little bit nasty. We can simplify it a little bit. Right, so I go, well, I know n choose 7 is n factorial over 7 factorial, n minus 7 factorial. All of this is times 6 factorial. times n minus 7 factorial. So I'm going to cancel that. I'm going to cancel most of that. I have n factorial over 7. That's the size of A. The size of my sample space is what? Yeah, so I have n factorial is the size of my sample space. So the probability of A is the size of A over the size of my sample space, n factorial over 7 over n factorial. This will cancel. I'm left with 1 over 7. Okay, so it's nice. It kind of worked out really great. Took us a little while to get there, but yeah. Questions? Yep.
Can you like assume from the start that the probability of A is 1 over 7?
I would at this point, yeah. If you see this question again, I would definitely do that.
Well,
And we'll show it for 6 as well. So this is
I'm guessing it's also 1 over 6.
yes. Yeah, that turns to 1 over 6. I'll prove it to you here, but yeah. So again, this is, I mean, I don't change these questions a whole lot if I do at all. You know, some of them are really just old questions. Actually, a lot of them sometimes. Depends how much time I have, basically how many of these questions I change. So if you see something like this, I would definitely jump right to there. Yeah, other questions? All right, so let's do probability of B. Let's do the size of B first. Same thing. Now that the minimum is found in location 6, well, I choose 6 numbers. I put the lowest one in location 6. I have 5 left to put in the other first 5 locations, 5 factorial. And then I have n minus 6 factorial. I have n minus 6 numbers left and n minus 6 locations to the right of my 6th position. All right, so, and then this again simplifies n factorial over 6 factorial, n minus 6 factorial times 5 factorial times. So these cancel out, that mostly cancels out. I get n factorial over 6. The size of the sample space is n factorial. So that means the probability of B is, and that's 1 over 6. Okay, so the probability of A is 1 over 7. The probability of B is 1 over 6. There's a simpler, more intuitive way to get it. I don't, but now you know. So yeah, now we want, well, what if they're both? So probability of A intersect B. So that means the minimum of the first 6 is in location 6, and the minimum of the first 7 is in location 7. So first I'm going to start by counting A intersect B. Oops. So again, I'm going to choose 7. I need to know the first 7 locations. So I'm going to choose 7 numbers. I'm going to put the lowest in location 7 and the second lowest in location 6. There's exactly one way to do that. Then I have 5 numbers left and 5 factorial ways to arrange them in the first 5 locations. And then I have n minus 7 factorial ways to arrange the rest of it. Again, we can simplify quite a bit here. We have n factorial over 7 factorial, n minus 7 factorial. Yeah, let's write it out. This cancels, this mostly cancels. I get 6 times 7 here. N factorial over 42. Then probability of A intersect B, well, of course, that's equals this over the size of the sample space, which is n factorial. And this is 1 over 42. And probability of A is 1 over 7. Probability of B is 1 over 6. So the probability of A times the probability of B equals 1 over 6 times 1 over 7. equals 1/42. So yeah, these are independent events. All right, so nasty, but again, if you see that question, I don't think you'll see it, but I would still, I could be trying to trick you. But yeah, if you see it again, you know how to compute the probability of A and probability of B very quickly. It's just A intersect B that I would be worried about. All right, questions? I think that. Yeah. Yeah, those are random variables. This is, I mean, 18 should be sort of pretty straightforward. Probability of A union B. Well, I have given enough information here. I know that probability of A union B is equal to the probability of A plus probability of B minus the probability of A intersect B. And that works even if the intersection is empty, because then that will be 0. Right, so this is your one-stop shopping for your expression for union. This also gives you the sum rule, just sort of implicitly. So probability of A I know is 1/4. What's the probability of B? Yeah, so it's using the complement rule. It's 1 minus 2/3, so it's 1/3. A intersect B. Well, how can we determine that? Yeah, so they're independent. So probability of A times probability of B is 1/12. And then, so what is that? 3/12 plus 4/12 minus 1/12, 1/2. So it's 6/12 or 1/2. So that's C for 18. Okay, so that's, I do have one other question I'd like to show you, but any questions about that? Yep.
Sorry, that equation is always true no matter what.
Yeah, because if the intersection is non-empty, then you have to compute it. If the intersection is empty, this will be 0. So yeah, it's the same as inclusion exclusion essentially, right? Inclusion exclusion is just the sum rule. And this is the same thing applied to probabilities. All right, other questions? All right, took most of the class. Okay. I just want to show you one more thing because you will probably most likely see something that looks like this, some algorithm that you have to analyze. So there's a couple ways to do this. It's up to you, I guess, how much you want to be challenged. But yeah, so this recursive algorithm, I feel like singing. What I would do, because this is basically pretty small, so you can draw the recursion tree, right? So that's sort of one way to do it. That's foolproof if you can't quite figure out what the pattern is here. The other thing you can do is look at some small values and build up to the larger values and see if there's a pattern. A lot of the times it's Fibonacci. Spoiler alert, although not always exactly Fibonacci, but something very close to that. But let's just go, if I'm strapped for time, here's what I'm doing. I'm saying, I'm drawing the recursion tree. I make a call to 9, F9. And then what happens? Well, if n is odd, so n is odd, then I feel like singing with n plus 1. So this actually just goes to 10. Recursively calls it on 10. I go back here, I say if n is odd, well, it's not odd any longer. So now I'm going to do this else statement. And then I call this twice. I feel like singing n/2, and I feel like singing n/2 minus 1. So n/2, 10/2 is 5. 10/2 minus 1 is 4. Okay, good. You're going to see some patterns in this recursion tree that you can take advantage of. But 5 is again odd. Right, so that means I feel like singing n plus 1, which means I call 6 here. And then from 6, I call 3 and n/2, and I call n/2 minus 1, so I call 3 and 2. All right, and then. I mean, it's not the easiest, but it's well, it's easy, a little bit painstaking. 3, 3 is odd, that goes to 4. Well, now I have a 4 here and a 4 here, so I just need to compute one of them, and I'll know both of those values. 2 is, I call it's even, so I feel like singing n over 2, which is 1, and then n over 2 minus 1, which is 0. N equal to 0 and n equal to 1, I sing O Canada. So the number of times I sing O Canada on a call to number 2 is 2. Okay, so if I see 2 again, I know that it makes 2 calls to, or I sing O Canada twice. All right, so then let's look at this 4. 4 is even, so I call n over 2, which is 2. Okay, so I know I make 2, I sing O Canada twice there, and then n over 2 minus 1, which is 1. I sing O Canada once there. So the number of times I sing O Canada here is 3. Right, which means this branch here, also 3. And so basically I expand it until I see all of the leaves, right? All of the base cases. But once I see a branch, once I see a call to, I feel like singing 4, it's always going to give the same result. So yeah, I have 3 here, 2 here, and 3 here. So it's, what is that, 8? Is that right? Or did I mess up someone? 4 is 3. Yeah, because I have 2 here, 1 here. Yeah, so it should be 8. Anyway, I would do something like that. Yeah.
Questions on the, will this ever turn, like, not terminate for a certain number? Like, we have to know that you wrote well.
Is there really? Will this terminate for a certain number?
I think there's like what's wrong with this or something, and there's only 2 options. And like, I don't know. It doesn't give a certain number. It just like asks you, is there?
Oh, is there any number for which it doesn't terminate? Well, you probably tell by my expression that no. I haven't actually seen a question that looks like that, to be honest. So.
What's wrong, like, on the midterm, like question 4 for this test, which we came off of the finals?
It's actually probably a combination, because I think, well, I mean, any of them are fair game. They're all pulled off Brightspace though, right? One of the Professor Morin at some point got really ambitious and put all of old McKeel's old test questions into Brightspace. So there's a huge random pool there. And I basically draw a bunch that I like, and then I change some numbers, as much time as I have. So it depends on how Pat entered them. I don't know. I think it's just the old finals, but I think it's just the old finals, but anything is fair game, right? I mean, it's the same basic questions anyway. Yeah. Okay. Other questions? Yeah. Whoa, that's yeah. So what happens? Sure. There's questions about the Fibonacci sequence that are okay. So let's say, what is it? I call Fibonacci 99. How many times does this call Fibonacci 95? I mean, you can draw this out, but let's think about it. If this is the Fibonacci, if this is indeed the Fibonacci series, so this is the 95th Fibonacci number. I don't know what it is, but how many times have I called this in my initial call to F99? Well, I can start building from the bottom up. I say, well, if I make a call to F95, then I make that call once, that's fine. If I call F96 and that calls F95 once, and then F94, right? If this is indeed the Fibonacci, I mean, read the algorithm carefully. If it is the Fibonacci algorithm, it'll look something like this. So that means in F96, I've called F95 once. F97, assuming I call F96 and F95. F95 is one call, F96 is one call, so then I make two calls here. F98, well, I call F97 and F96. F97 is two, F96 is one, so that's three. So you can kind of build up, and you know, it really is just the Fibonacci sequence. Read the algorithm carefully though, because this is also the Fibonacci sequence, may not be as obvious, but yeah. Questions on this, and then we might as well keep going with this for now until I run out of stuff, but all right, so I'm going to look at another way to solve this. If you want to try and spot a pattern, is to start from the bottom up. Okay, so if on a call to 0 or 1, right? So F0 or 1, I single Canada once. If I call F2, well, what does that do? Then 2 is even, so I call F1, and then I call F0. Both of those, I single Canada once, so F2 is equal to 2. F3, well, that's really just equal to F4, right? So F3 is odd, so I add 1 to here, and then F4 calls F2 plus F1, which is 2. I single Canada twice in this call to F2, and I single Canada once in the call to F1, so that's 3. So I have, yeah, F3 is equal to F4. So what I end up with is sort of this pattern is then F5 is equal to F6, which is equal to, well, F6 I call F3 plus F2, so it's 3 plus 2, which is 5. So I start at 1 for these two numbers, and then 2 for these, yeah, well, 2 here, I guess, by itself. F3 and F4 are both 3. F5 and F6 are both 5. F7 and F8 are both 8, right? We end up adding 3 plus 5. So it's the Fibonacci sequence is just sort of hidden a little bit. Yeah, that's the other way to do it. That's what I would do, but if you're comfortable analyzing those and finding the patterns, then you can do that as well. Yeah, just be careful. It's real easy to be off by 1 doing it like that. Okay, this is yeah, okay. Well, it's 6 after. I don't know. Are you guys want to see more questions, or are you guys? Yeah. Sure. All right. I think we have time. We can burn one lecture. All right. So then assume we have a multiple choice exam that has 25 questions. For each question, 4 options are given to you, and exactly one of these options is the correct answer. Assume that you choose all random answers. What is the probability that you have exactly 17 out of 25 correct answers? Well, this is very, very similar to, well, I guess the coin flips earlier, but so here, the probability that I get a correct answer. So let's say, yeah, let's say CI is that I get question I correct. And that has probability 1/4, right? I choose uniformly at random. There's exactly 1 out of the 4 that are correct. So the probability that I get question I correct is 1 out of 4. And then the probability that I don't, let's call it CI naught, that's 3/4. And then I say I answer 25 questions by guessing, and 17 of them I get correct. Okay, so yeah, I answer 25. 17 of them I get correct with probability 1/4. And then what is that? 8 of them I get wrong with probability 3/4. So 17 plus 8 is my 25 original questions. But that's just one precise arrangement, right? So maybe I get the first 17 right and the last 8 wrong, but what if I get the first 8 wrong and then the last 17 correct? So I have to count all possible arrangements. And, this is, again, these are all outcomes. And so, yeah, I sum them up in order to find all of the ways that I can get 17 correct and 8 wrong. And that would be, well, I mean, really, it's a big spoiler. 25, choose 17 ways to arrange my 17 correct questions and my 8 incorrect questions. All right, so then it would be, yeah, this one, C. All right, I don't know if there's any other good ones in. I want to. Gotta be careful. I'm going to be giving you actual answers at some point. Palindrome, sure. Actually, let's do 13. I think that's it's conditional probability, so it involves regular probability as well. So it's a good practice question. So I have a set X of 10 numbers, and I choose a uniformly random subset of X. All right, so how do I choose a uniformly random subset of X? So we'll talk about that. And then A is the event that Y contains at least 4 elements, and B is that all elements of Y are even. And what is probability of A given B? Well, probability of A intersect B over the probability of B. Okay, so the probability that all elements of Y are even. Oh, that's easy. It's maybe a little trickier than. Okay, so probability of B is basically the size of B over the size of the sample space. How many subsets can I choose from this set? How many sorry? That's subsets of size K, yeah. But now these are any subsets. So from 0 all the way up to size N and anything in between. I can have all of the subsets of size 1 and all of the subsets of size 2, right? So one of them is that, one of the events is Y contains at least 4 elements. So we have to talk about all different sizes. So yeah, how many subsets are there of a set? Yeah, so there's 2 to the power N. So 2 to the power N, 2 to the power 10 here. Okay, and B is all the elements of Y are even. So how many subsets can we choose from X that are all even? Well, in some sense, I'm just looking at, instead of looking at X, let's look at X prime is equal to 2, 4, 6, 8, and 10. So there's 5 elements in X prime that I can choose from. So now I want all of the subsets from X prime, which is 2 to the power 5. Okay, so we have probability B, probability of A and B. Now I want all of those that contain at least 4 elements, right? So, yeah, probability of A and B. is what happens when you go off script. You got to think on your feet. So this is something over 2 to the power 10. So A and B, again, you can think of it as I'm selecting from X prime. So there's 2 to the power 5 possible, but I want all of the subsets that I have at least 4 elements. Okay, so there's 5 total, so I can choose all of the subsets of size 4. Right, so there's 5, choose 4 of those. Plus all of the subsets of size 5. And there's 1 of those. 5, choose 5 or 1. Okay. So yeah, we can get rid of these big numbers. So let me write that out explicitly. Probability of A intersect B equals 5, choose 4 plus 1 over 2 to the power 10 over probability of, A given B. So it's then the probability of A intersect B over the probability of B, which is 2 to the power 5 over 2 to the 10. These will cancel out. 2 to the power 5 is actually 32. 5, choose 4 is 5. So I get 6 over 32. All right, so it's not as bad as I thought. 6 over 32 is 3 over 16, right? So I get A here. All right, so the big nasty 2 to the power 10 canceled out, and we're left with something I could compute by hand. That's, all of these you should technically be able to compute by hand. You're allowed to bring in calculators, but yeah. So if you end up with a huge number that you can't compute by hand or cancel something out, maybe, maybe you're not doing it correctly or whatever. All right, questions? All right. 2 bit strings, each of length n. In both bit strings, each bit is 0 with probability 1/2 and 1 with probability 1/2, independent of all the other bits. So these are 2 random bit strings. And then we're going to make this is basically very similar to the one we did already. But the answer looked different. So yeah, what is the probability that each element in this string is non-zero? So A1 plus B1. First of all, what is the probability that any element is non-zero? Anybody figure that out off the top of their head? All right, so let's draw it out. So AI, BI, and then we want to take AI plus BI. So we look at all possibilities, 0, 0, and 0, 0, 1, and 1, 1, 0, and 1, 1, 1, and 2. So what's the probability that in this new string that any given bit is non-zero? Yeah, it's 3/4, right? So it's simply, this is the only outcome where it's 0. So I have 4 outcomes. They're all uniformly, it's a uniform probability space. Or you can, you can compute the probabilities. They're each 1/4, right? It's just the probability that AI is 0 times the probability that BI is 0. And we said they're each 1/2. So yeah, the probability, let's call this CI. CI is greater than 0 is equal to 3/4. Okay, so what is the probability that every element in this string is non-zero? And then the probability that CI equals 0 is 1/4. So every string is, every element is non-zero. Which one do we like here? Yeah. D. Does D make sense? So we don't need, so this would imply complement rule, but we don't need the complement rule. We can count directly. Every element is non-zero with probability 3/4, and there are n of these elements. So yes, it's just, the first one is non-zero and the second one is non-zero, and they're all independent. So it's 3/4 to the power n. All right. Calculator supports choose function computation. We could use that. No, you can use the choose function. I'm not going to around and check. Just yeah. Yeah, definitely. If I was writing this, I would use my calculator and I would use the choose function. So yeah, go for it. All right. Other questions? All right, John, this should be very well prepared. Yeah, I mean, any of these are fair game. We got time for one more, let's say. Which one? You see any you like? Yeah.
That was, something like you see like the string, like somewhere, that means like what about like a free strings.
A free string. So let's say we have an alphabet of A, B, and C, or it could be A, B, C, D. And let's find the number of, what do you want? A free strings defined recursively. There are a lot of questions available like that. Some with little tricks like the 0, 1, 1, where every second one, so you have one case that's just a constant and the other is recursion. But this is pretty straightforward. I'm simply going to start. I want a recursive formula for the number of A free bit strings of length n, right? So there's some base case. I'm going to say, I'm going to give you some number n greater than or equal to 3, probably. All right. So I'm going to, again, just look at all the possible cases. I'm just going to start writing a bit string. I'm going to say, well, it can start with a B, right? And then anything else is fair game. So that is, there's S of n minus 1 A free bit strings that start of length n that start with a B. And then I can do the same thing for C. There's Sn minus 1 of those as well. Other than that, I can start with an A, but now I'm restricted. All right, so we can start with 2 of Sn, 2 times Sn minus 1. So that accounts for these guys. So what if it starts with an A? Well, if it starts with an AB, well, then anything after B is okay. Right, so this is S of n minus 2 now, because I've decided on the first 2 locations. But then from here on, I can put whatever I like as long as it's A free. This is going to be a bit of a pain, but or if I start with an AC, right? If I start with AC, then everything afterwards is okay. It's fair game. Because after this C, I can put another A, I can put whatever I like, as long as it's A free. So I get 2 times S of n minus 2. All right. So now I'm left with A. And now at this point, I've decided on the first 2, and I can't put an A in that last location, right? So I can put a C. Or sorry, well, let's keep it in alphabetical order. I can put a B here, at which point everything that's left is fair game, and it's size n minus 3. Or I can put a C. And then again, everything that's left is fair game, and it's size n minus 3. And so this is 2 times S of n minus 3. Okay, so these are all very straightforward. Basically, this extends to an alphabet of any size, and any, A free B free, C free. Those will all work. Those are all very straightforward. If you see something like this, that doesn't work so well. If you see something like this, I'm telling you, there's a trick, because this is not fun to compute. Really, everyone that's taught this class has tried to ask this on, or thought about asking this on an assignment and tried to work it out and then just went, wow, no way. So yeah, there's always a catch if you see something like this, like 0, 1, 1, things like that. But yeah, questions on that? All right, so I think we will stop there. The next class. Yeah, the next class is the test. I guess I'll do this all again tomorrow morning, but yeah. 17 questions on the test. Yep.